Hello, welcome. In this video, I'm going to be looking at almost exact equations, right? In the last one, I talked to you about exact equations and a technique we could use to find kind of an implicit solution to, a particular, to some kind of differential equation where, maybe we were or were not going to be able to solve for explicitly y as a function of t. Okay, now this one, I want to suppose that it's not exact in the sense that, I don't remember if I was, super specific about what I meant by exact in the last video, but kind of the test for exact is if my equals nt. Okay, suppose it's not exact, but it's kind of close. There's going to be a way we can deal with this. What we're going to do is we're basically going to take the exact equations approach and modify it in the same way that we did the integrating factor a few videos ago. So what we're going to do is we're going to say that this is not exact, but I'm hoping that I can find some sort of mu, which is going to be a function of t and potentially y. As you'll see, it's actually going to be one or the other, but it's going to be some function that we can multiply, on both sides of this differential equation to make it exact. So kind of the new situation I'm interested in is mu times m plus mu times n y prime is equal to 0. This is the situation now. Now, in order for this to be exact, what I'm going to need is I need the derivative of this with respect to y to be the same as the derivative of this with respect to t. Okay, so maybe that's so important. I'm going to switch up the color and maybe I'll just really use blue. Okay, so what I'm going to say is for this to be exact, I'm going to need the derivative of this with respect to y, mu m y, to equal the derivative of that with respect to t. So mu n t. That's what I'm going to need. And so what I'm going to do is I'm going to actually take these derivatives, using the product rule. Okay? These partial derivatives. So I'll have the derivative of u times m with respect to y. It's going to, I'll just take the derivative of mu first and leave m the same, and then add n, taking the derivative of m and leaving mu the same. Okay. And then I'll do the same thing over here. Okay, so I'll say derivative of mu with respect to t, leave n the same, plus derivative of n with respect to t and leave mu the same. Now what I'm going to do is I'm going to collect these two things to one side and put those two things on the other. Okay? So what I'm doing is I'm subtracting this from both sides, and then I'm going to, after that, subtract this from both sides and kind of group them up in a nice way. So when I get all the things with mu on one side, I'll have mu times, and this might be the point, let me just check. This is where I'm going to just start calling this my minus nt, and that's going to be equal to, I still have this partial mu respect to t n, and then I'm going to subtract away this thing, partial mu respect to y times m. Now, this is basically the equation that we have to solve for mu to find our integrating factor. And, well, first of all, I'll just tell you this is not an easy differential equation to solve. And second of all, this is a partial differential equation, right? And at this point, we're only talking about ordinary differential equations. In this class, we're only going to talk about ordinary differential equations. So, this is a PDE, and this is not really going to be the type of thing we're going to be able to solve. Because this differential equation is at least as difficult to solve as that one when it wasn't exact. That's what I'll say. At least as hard. Okay, and we want to make this easier, right? This whole point of what we're doing here is to make solving differential equations easier. So what I'm going to do is I'm going to say, okay, this is maybe a little too much for where we are right now. But what if mu was not a function of both t and y, but was instead just a function of t? So let me color here, but I think I'll just say, yeah. Okay, if mu is a function of t only, then this would be 0, right? That partial derivative of mu with respect to y. And as a result, that whole thing would go away. Moreover, if mu is then just a function of t, then the partial derivative of mu with respect to t, I mean, you could say it, but you could also say it's the derivative of mu with respect to t, like in the Cal1 sense. And that'll be actually really helpful for us because that'll turn that into a separable differential equation, and then it'll be something we can solve. So I'll have mu times my minus nt, and that will be equal to, this is going to become the derivative of mu with respect to t times n minus 0. And then, okay, this is the type of thing, it doesn't look as separable when I don't write it as d mu dt times n is equal to mu times my minus nt. And maybe that doesn't look separable to you even now, okay? But if I was to multiply both sides by dt and divide both sides by mu, and I guess I'm going to need to divide n out of there also, I'll have 1 over mu d mu equaling my minus nt divided by n dt. Okay. Now this thing, I can't solve this in general. I can't anti-differentiate this in general. I don't know what my and nt are. I sure don't know what n is in general. So I'm just going to have to suppose I can anti-differentiate. Okay. I kind of hoped I could solve that all in that space, but that's not going to be possible, so I'm going to move up here. Okay, we know how to deal with 1 over mu d mu. That's going to be log absolute value of mu equaling the antiderivative of that with respect to t. So I don't really have anything to do, so I'm just going to call it the antiderivative with respect to t. So my minus nt all divided by n dt. Okay. Let's see. I'm going to just, I think y'all know how it goes from here. I'm going to skip a couple of things along the way. So mu is going to be equal to e to the, and it's really going to be c times e to the antiderivative of that. But as you remember with the previous situation with exact equations, with the integrating factor, if I go and use the integrating factor and I put it everywhere, I could then divide away the c everywhere and I don't even need to worry about it. So I've got my minus nt divided by n dt. That's what mu is, okay, on one hand, right? If mu were a function of t only, then I would have this. Okay? So what I'm going to do is I think I'm going to clear this all out and just like kind of put the result in there. And then I'm going to actually do the same thing for if it was a function of y only, just so I'm not, going to leave anybody behind. I mean, it is very similar, but there is a slight difference in the formula, so I just kind of want to show you where that comes from. So, okay, I'm going to clear this out. Put the formula. If mu were a function of t only, mu of t equals e to the antiderivative of my minus nt divided by n dt. Okay? But if mu were a function of y only, okay, this would go to 0, right? Okay. So I'd have, and then that would become it would become a d mu dy. And then I'm going to actually write this over here on the left just to make it look nice like I did before so you can, kind of know that it's going to be separable. And then I know that I'm not It's going to look very similar to that, but it's not going to be the same, so I'm just going to clear it up preemptively. So I've got mu times, no, I'm going to write it over here. So negative d mu dy times m is equal to, what is it, mu times my minus mt. Okay, then I could kind of separate variables, right? I could say 1 over mu d mu equaling, okay, I got to deal with this negative, so I'll just deal with that by kind of moving, nt minus my. So that would be nt minus my. I'm going to have to divide by that m, and then, wait, yeah, dy. And then I'm going to move up here, and I'm going to say I can anti-differentiate that, so it'll be, log absolute value of mu equals antiderivative of nt minus my divided by m dy. Then, skipping a little bit of algebra, I'm going to have mu of y is equal to e to the antiderivative, really c e to the antiderivative of nt minus my divided by m dy. Okay? And so I'll just kind of write in that result here, and then I'll work an example for you. Okay? So in that case, mu of y equals e to the antiderivative of my minus nt. That's it. Nope, it's the opposite. Nt minus y. Could have just looked up above and seen that it was the opposite. Over m with respect to y. Okay. The thing is, what was I going to say? It's pretty obvious which of these you should use, based on the context. I am definitely going to choose an example to where, if you choose the wrong one, it's not going to work. You'll know. But what? I think I had something else to say about this. I don't know what it would be. Okay. It would come in a working example. All right. So, for example, let's see, what do I have here? All right. 2ty dt plus y squared minus 3t squared dy. Y squared minus 3t squared dy equals 0. All right, and okay, so this one is like, okay, you're gonna have to divide everything by dt first, yeah. And so I'll say, I'm just gonna work this in yellow. So I'll say 2ty plus y squared minus 3t squareds, okay, dy dt is y prime, is equal to 0. Okay, this is looking like the type of thing that I need to check to see if it's an exact equation. So what I'll do is I'll take the derivative of this with respect to y. Okay, so I'll say that that's m, and that is n. So my is going to be equal to 2t, and nt is going to be equal to negative 6t. Okay, these are not the same, therefore this equation is not exact. Okay, so what I'm going to do is I'm going to try to use an integrating factor. Okay, so all I see is t's here, so I'm thinking, I might as well do the one where it's in terms of t only, right? That would be your natural thought. That would be my natural thought. I hadn't worked one of these in quite a while, so that was my first thing I tried, and it didn't work. Okay, let me show you what happens. If I was to use, mu of t, that's going to be e to the antiderivative of my minus nt, 8t, over n. Okay? N is this y squared minus 3t squared dt. Now, I don't know about you, but I look at that integral and I'm not seeing a technique to deal with this like right off the top of my head. And that's kind of the thing here. And it's at this juncture, it's tough for you to know like what is too hard and what is what you're supposed to be doing. But at this point, if you're not seeing anything to do, it's probably down the wrong road, right? So let's just scrap that and consider using the other one, that one. And maybe instead of putting e to the and trying to fit that integral in a really small exponent, what I'll do is I'll just say the exponentiation of antiderivative of nt minus my, that's going to be negative 8t, divided by m is 2ty. And I want to integrate that with respect to y. And this is much better, right? Because of, because of that. Right? So this is negative 4 over y. So this is antiderivative of negative 4 over y is going to be negative 4 log absolute value of y. What I'm going to do is I'm going to kind of rearrange this, e to the log of y to the negative 4 power. And that's e to the log of absolute value of y is going to be absolute value of y. But then if I take absolute value of y to the negative 4th power, that's just going to be 1 over y to the 4th, regardless of what y was in the first place. And I feel pretty good about this. This is going to be a good integrating factor. Okay. And I think I'm in the interest of showing you all the steps, but not cramming them into too little space, I'm just going to get rid of that and call it 1 over y to the 4th. Right, and then what I'm going to do is I'm going to, just like before, I'm going to multiply everything by that mu, that 1 over y to the 4. So I have 2ty over y to the 4 is 2t over y to the 3 plus, okay, if I divide all of that by y to the 4, I'll have 1 over y to the 2, and minus 3t squared over y to the 4th. Y prime equaling 0. Okay. Now, just kind of to quickly check to see if this is exact, to make sure I've done this right, I need to take the derivative of this with respect to y. So that would be negative 6t y to the negative 4. And that needs to be the same as what I get over here when I take the derivative with respect to t. And sure enough, I get negative 6t over y to the 4. And I mean, to me, that's very surprising. It even works. But this equation is now exact. And so I'll be able to, I know that the solution is going to look like f of t and y equals c, where ft is equal to that and fy is equal to this. So my conclusion is going to be that f can be written as the antiderivative of this with respect to t. So, okay. And that'll be t squared over y to the 3 plus some constant function of y, which hopefully I'm going to find, in the process of my computations over here. Okay. Then, on the other hand, f is going to be equal to the antiderivative of, what is it, this thing with respect to y. So, y to the negative 2 minus 3t squared over y to the 4, maybe 3t squared y to the negative 4, make this a little easier, dy. And then that's going to be equal to, let's see, bump up the power by 1, divided by the new power is negative y to the negative 1. Just looking like part of my constant function of y at least. And then this is going to be, when I bump up the power by 1, that'll become negative 3 divided by negative 3, and then just be plus t squared over y to the 3. Which, okay, I'm already seeing that, so that's good. Plus some other constant function of t. Okay, looks like that constant function of t is going to be, it's going to have to be constant, because if I took the partial derivative with respect to t, I'd need to see it show up right here, and I wouldn't. So I'm going to conclude that that's part of my constant of integration that I'm going to see right here. And so I'm going to conclude that I can kind of like, merge these together. I've got t to the 2 over y to the 3, a negative 1 over y, and that's going to be all. Yeah, minus 1 over y is equal to c. And if this came with an initial condition, I could go ahead and find out what that c is. Say that y of 1 was equal to 1, I think that would mean that c was 0. But this is almost exact equations. This is exact how you deal with a differential equation that's not exact, but it's kind of close, and we can use an integrating factor to make it exact. Get ourselves a nice implicit solution. Okay? And that's all I got for you.